Hello, and welcome to another lesson from Math 1314 College Algebra. Today we will be discussing radicals and rational exponents. In this section, you will evaluate square roots, use the product rule to simplify square roots, use the quotient rule to simplify square roots, add and subtract square roots, rationalize denominators, and use rational roots. So we'll start with evaluating square roots. So when the square root of a number is squared, the result is the original number. Since 4 squared is equal to 16, the square root of 16 is equal to 4. The square root function is the inverse of the squaring function, just as subtraction is the inverse of addition. So to undo squaring, we usually take the square root. So it is the case that if a is a positive real number, then the square root of a is a number that when multiplied by itself is equal to a. So the principal square root of a is written as radical symbol with an a underneath. Now the whole thing, this whole piece, that is the radical expression. The a, that portion, is called the radicand, and then the red bar is the radical symbol. Let's do the definition. The principal square root, that's what we're defining. The principal square root of a is the non-negative number that when multiplied by itself equals a. It is written as a radical expression with a symbol called a radical over the term called the radicand. So let's do an example. Let's do an example using the product rule to simplify square roots. Let's start with the square root of 300. And our directions are to simplify. Well, we can rewrite this as the product of two separate radical expressions if we know a perfect square, particularly, that will help us simplify. Well, we know that 100 times 3 is 300, so the square root of 100 times the square root of 3 is another way to rewrite this expression. And so what we can do is simplify the square root of 100 to be 10, and that's 10 times the square root of 3. Okay, let's do a little more complicated example. What if we have the square root of 50 x squared y cubed times z? Do we have any perfect squares in this expression? Well, we have 25 times 2. That is one way we can break this down. X squared is a perfect square. Y cubed can be written as y squared times y, and then z. And we can separate these into separate radical expressions. Square root of 25 times the square root of x squared times the square root of y squared times the stuff that is not a perfect square, which is 2, y, and z. Well, the square root of 25 is 5. Five times the square root of x squared, which is x, times the square root of y squared, which is y, times the square root of 2yz, which is our final answer. Let's do one more example. The square root of 162 a to the 5th times b to the 4th. Well, we can simplify this because we know that 162 is 81 times 2. So we'll separate this to 81. We're going to have two separate expressions, 81 times 2. And then a to the 5th can be broken down as a to the 4th and an a. Those factors can be separated. And b to the 4th. So what we have is factoring the perfect square from the radicand. Well, the square root of 81 is 9. The square root of a to the 4th is a squared. And the square root of b to the 4th is b squared times the square root of 2a. And that's our final answer. Another thing that we can do if we have a product of multiple radical expressions, we can use the product rule to combine them into one expression. So what we can do is express the product as a single radical expression and then simplify. So consider this example. The square root of 12 times the square root of 3. Well, we can rewrite that as the square root of 12 times 3, which is the square root of 36. Can we simplify the square root of 36? Yes, we can, because it is equal to 6. 6 squared is 36. Let's try another example. Simplify the square root of 50x times the square root of 2x when x is greater than 0. We have to have x greater than 0 because that guarantees that what's under the radical, the radicand, for both cases is positive or non-zero. Okay, so we can simplify this. Let's rewrite it once. Times the square root of 2x. We can rewrite that as the square root of 50 times 2, which is 100, and x times x, which is x squared. What does that give us overall? Well, that gives us the square root of 100 times the square root of x squared. We could do that all in one step if we wanted, but the square root of 100 is 10, and the square root of x squared is x. And that's our final answer. So similarly to how we can rewrite the square root of a product as the product of the square roots, we can also rewrite square roots of a quotient as the quotient of square roots. So as an example, if we had the square root of 5 over 2, that's the same as the square root of 5 over the square root of 2. So in general, the quotient rule for simplifying square roots is as follows. This is a definition. The square root of the quotient a over b, a divided by b, is equal to the quotient of the square roots of a and b, where b is not equal to 0. So in other words, we write this as the square root of a over b is equal to the square root of a over the square root of b. So, if we are given a rational expression, how can we use the quotient rule to simplify it? Well, first we will write the expression as the quotient of two radical expressions, and then separately we can simplify the numerator and the denominator in separate pieces. Let's do an example. Let's simplify the radical expression, the square root of 5 over 36. The first thing that we do is we write this as a quotient of two radical expressions. So in the numerator, we have the square root of 5 divided by the square root of 36. And how can we simplify? Well, the square root of 5 in the numerator can't be simplified further, but we know that we can simplify the square root of 36 because the square root of 36 is just 6. So that's our answer, 5 over the square root of 5 over 6. Let's try another example. What if we start with 2x squared divided by 9y to the 4th? Again, what's our first step? We need to write it as the quotient of two radical expressions. So in the numerator, we get the square root of 2x squared, and in the denominator, we get the square root of 9y to the 4th. Okay? Are there any perfect squares in the numerator? Yes, there are. X squared is a perfect squared, so we're left with, in the numerator, the square root of 2 times x divided by, do we have any perfect squares in the denominator? Well, both of those are perfect squares. The square root of 9 is 3, and the square root of y to the 4th is y squared, which is our final answer. So what if we want to go the other direction? What if we start with two square roots and we want to combine those into a single square root to simplify? So let's take an example. What if we start with the square root of 9a to the 5th b to the 14th power divided by the square root of 3a to the 4th b to the 5th power? So instead of rewriting a single quotient as the quotient of two radicals, we want to rewrite two radicals in a rational expression as a single radical. So we can write that as a single radical, and it's 9a to the 5th b to the 14th over 3a to the 4th b to the 5th. Now we can use the things we know about exponents to simplify further inside the radical. We know that 9 divided by 3 is just 3. We can use the quotient rule of exponents to say that a to the 5th divided by a to the 4th is 5 minus 4, which is a to the 1st power. And b to the 14th over b to the 5th is b to the 14 minus 5, which is b to the 9th power. Do we have any perfect squares? Well, we're going to be left with a square root of 3 times a. That's not a perfect square. But we do have the square root of b to the 9. That's not a perfect square, but it contains one. So we rewrite it one more time as 3a, square root of 3a times the square root of b to the 8th power times the square root of b. That leaves us with the square root of 3ab times b to the 4th power. B to the 4th times b to the 4th gives me b to the 8th, and that's my final answer on this problem. So we've talked about multiplying and dividing to simplify square roots. Let's move on now and talk about adding and subtracting square roots. Adding and subtracting square roots. So we can add or subtract radical expressions only when they have the same radicand, that's the part under the radical sign, and when they have the same radical type, such as square roots, which we've been discussing. So if we wanted to add, for example, the square root of 2 and 3 times the square root of 2, we would be able to do that because the part under the radicand, is 2 in both cases. We have 1 times the square root of 2 plus 3 times the square root of 2, which gives us 4 times the square root of 2. It's often possible to simplify radical expressions, and that may change what we have under the radical as the radicand. So let's take, for example, the square root of 18. Well, it has a perfect square as a factor, and that's 9. So you have the square root of 9 times the square root of 2, which is equal to 3 times the square root of 2. So now we would be able to rewrite the square root of 18 as the 3 times the square root of 2. So imagine we started at the beginning and we have the square root of 2 plus the square root of 18. Well, initially you would think, well, they don't have the same thing under the radical, so I can't do this problem. Well, what you can do is simplify that to the square root of 2 plus 3 times the square root of 2, because the square root of 18 can be simplified to 3 square root of 2. So let's consider another example where we're doing this more generally. If we're given a radical expression that requires addition or subtraction of square roots, and we need to simplify it, we first need to simplify each radical expression. So example, simplify and add. So let's imagine that we have 5 times the square root of 12 plus 2 times the square root of 3. Again, this looks like we can't do this problem because they have different radicands. But it turns out that we can simplify that radical to be 5 times the square root of 3 times the square root of 4 plus 2 times the square root of 3. Well, the square root of 4 is a perfect square, so we end up with 5 times 2, the square root of 4, which is 10, times the square root of 3, plus 2 times the square root of 3. Well, 10 times the square root of 3 plus 2 times the square root of 3 is just 12 times the square root of 3, and that's our final answer. Let's try another example. Let's imagine that we have the square root of 5 plus 6 times the square root of 20. Again, we have different radicands, but do we have a perfect square that we can simplify that second radicand? We do. The square root of 5 stays the same, and we're left with 6 square root of 4 times the square root of 5, which we can rewrite. The square root of 5 plus 6 times 2 times the square root of 5. Didn't skip that step this time. The square root of 5 plus 6 times 2 is 12 square root of 5. And then 1 square root of 5 plus 12 square roots of 5 is 13 square root of 5. And that's our final answer. Similarly, we can subtract square roots. Let's try an example. 3 times the square root of 80x minus 4 times the square root of 45x. Now those seemingly don't have the same radicand, so we wouldn't be able to do this, right? Well, we can probably simplify those radical expressions first and have the same radicand where we can simplify. Do we know any perfect squares that are factors of 80? Well, I know that the square root of 16 times 5, 16 times 5 is 80, so that works. Do I know any perfect squares that are factors of 45? Well, 9 times 5 is 45, and 9 is a perfect square, so we can simplify one more step. 3 times the square root of 16 is 3 times 4. 3 times 4 is 12 times the square root of 5x minus 4 times the square root of 9. 9 is a perfect square, so we can do 4 times 3, which is 12. And then we're left with the square root of 5x. Do those have the same radicand? Well, they do. It's 5x. So we can perform the subtraction operation here. Well, what's 12 times the square root of 5x minus 12 times the square root of 5x? Well, 12 minus 12 is 0 times the square root of 5x, and anything times 0 is just 0. Now that we've talked about multiplying, dividing, adding, and subtracting expressions that contain square roots, let's now talk about rationalizing denominators. So when we have an expression involving square root radicals that are written in simplest form, it will not contain a radical in the denominator. So the way that we can remove those radicals in the denominator of a fraction is called rationalizing the denominator. We know that multiplying by any value equal to any value multiplied by 1 doesn't change the value. We use this property of multiplication so we can change expressions that have radicals in the denominator and remove them by multiplying by a clever 1. So for a denominator containing a single term, we can multiply by the radical in the denominator over itself. So if we have a denominator, and I'm going to use 1 over b times the square root of c, considering just the denominator part, b square root of c, we can multiply by the square root of c divided by the square root of c. That's just equal to 1, so we're not changing the value overall. Now, if there's a sum or difference of a rational and irrational term, then we must multiply the numerator and denominator by the conjugate of the denominator. And the way we do that is by changing the sign on the radical portion of the denominator. So in the denominator, if we have a plus b square root of c, then we would need to use the conjugate to multiply by it, which is a, and we change the sign from plus to minus, b square root of c divided by a minus b square root of c. So we'll go through examples of what this means. So first, if we're given an expression that has a single square root term in the denominator, we will rationalize by multiplying the numerator and denominator by that radical term. So let's consider an example. If we have 2 times the square root of 3 over 3 times the square root of 10, how would we get rid of this square root of 10 in the denominator? Well, as we were told just a minute ago, we need to multiply by the radical expression in the numerator and the denominator of a clever 1. This allows us to simplify. That gives us 2 times the square root of 3 times the square root of 10 divided by 3 times the square root of 10 times the square root of 10. We're multiplying 2 square roots together that are the same thing. That gives us just 10, or 3 times 10, which is 30. So we're left with 2 times the square root of 3 times the square root of 10 over 30. Can we simplify that further? Well, we have 2 over 30, so that gives us 1 over 15. So 15 is our denominator, And we can combine those two radical expressions using the product rule to make that the square root of 30. So the final answer is the square root of 30 over 15. Let's do one more example where we write this in simplest form. Let's do 12 square root of 3 divided by the square root of 2. Similarly to what we did before, we need to multiply by a clever 1, and that's the radical in the denominator. So we have the square root of 2 over the square root of 2. Well, in the numerator, the result is 12 square root of 3 times the square root of 2 divided by the square root of 2 times the square root of 2, which is just 2. Okay, again, we can combine this. 12 divided by 2 is 6, and the square root of 3 times the square root of 2, there are no perfect square factors there, so we can rewrite that as 6 times the square root of 6, and that's our final answer. Now that we've talked fairly extensively about square roots and their properties, let's talk about other roots. Let's talk about understanding nth roots. Suppose we know that a to the third power is equal to 8. We want to find a number that when raised to the third power is equal to 8. Well, we know that 2 to the third power is equal to 8, so we say that 2 is the cube root of 8. The nth root of a is the number that when raised to the nth power gives a. For example, -3 is the fifth root of -243 because -3 raised to the fifth power is equal to -243. So if a is a real number with at least one nth root, then the principal nth root of a is the number that has the same sign as a when raised to the nth power equals a. So let's write that definition. Let's say it again. If a is a real number with at least one real, one nth root, then the principal nth root, written as the nth root of a, is the number with the same sign as a that when raised to the nth power equals a. Notice the number by the radical sign here is n instead of not having a number there. With the square root, we understand that if there's no number, it is a square root, but now we're talking about roots other than square roots. So the index of the radical is n. So what did we just define? We just defined the principal nth root and the index of the radical. Let's do an example. Let's take the fifth root of -32. Well, the fifth root of -32 is equal to -2 because -2 raised to the fifth power is equal to -32. Let's consider another example. What if we have the cube root of -216? Remember, in our definition, it has to have the same sign as our original number. What is the cube root of 216? Negative 216, that is. What number raised to the third power gives us negative 216? Well, negative 6 raised to the third power gives us negative 216. So negative 6 times negative 6 gives us 36, and then times a negative 6 will give us 216. Okay, let's try one more example. What if we have the fourth root of 4 times the fourth root of 1024? Well, that's two separate radical expressions, so we want to first write it as a single radical expression. So we can rewrite that as the fourth root of 4 times 1024, which is 4096. Well, 8 to the fourth power is equal to 4096, so the fourth root of 4096 is 8. Now that we've talked about square roots and then nth roots, we can now use rational exponents to rewrite radical expressions. We can rewrite radical expressions without the radical symbol as fractional exponents. Now the index n has to be a positive number, positive integer, and if that index is even, then a, the part that's under the radical, the radicand, cannot be negative. So, if n is an integer, it's the definition. If n is an integer and a is a real number, then a raised to the 1 over n power is equal to the nth root of a. If n is even, then a must be non-negative. Also, we can have rational exponents with numerators greater than 1. In these cases, the exponent can be a fraction, and it must be a fraction in lowest terms. So we raise the base, a, to the power, and then take the nth root. The numerator tells us the power, and the denominator tells us the root. So, rational exponents can express principal nth roots in the following way. The general form for converting between a radical expression and to one with a rational exponent instead is a to the m over n power can be rewritten as the nth root of a quantity raised to the m power using exponent properties, or we can write it as the nth root of a to the mth power. So if we are given an expression that has a rational exponent, we can also work the other way and rewrite it as a radical. So the first step in doing so is to determine the power by looking at the numerator and the root by looking at the denominator. So let's do an example. Write 343 to the 2/3 power as a radical, and then simplify. So first we know that if we look at the power, we can find the exponent. So we can say 343 raised to the 2 power under a radical. We'll go there. We want to have that in parentheses. Actually, let's rewrite that. We can say that 343 to the 2/3 power is equal to a radical. So the power of the whole thing is raised to the 2 power because that's the numerator of the rational exponent. And then the denominator is the root, which is 3, so that's the 3rd root of 343 raised to the 2nd power. Another way we could write that is the cube root of 343 squared. But we know that the cube root by itself, the cube root of 343 is 7, because 7 to the 3rd power is 343. This cube root is easier for us to find, and it's a whole lot easier than taking the square of 343 and then taking the cube root. So in general, it's easier to say this is equal to 7 squared, which is 49. It's easier to take the root first in most cases. Okay, let's try another example. We want to write 9 to the 5/2 power as a radical. Again, we know what the root is by looking at the denominator, which is 2. We could leave that off since it is there, but then we can then take the 9 as the base in there and raise the whole thing to the 5th power. We generally want to take the root first. What is the square root of 9? Well, that's just 3 raised to the 5th power. What is 3 raised to the 5th power? Well, that's 3 times 3 times 3 times 3 times 3. Well, that's 9 times 3 times 3, which is 27 times 3 times 3, which is 81 times 3. And what does that give us? What is 81 times 3? 243. Now let's try simplifying something that has a rational exponent and has variables. Let's write a radical as a rational exponent. Let's now do an example where we write a radical as rational exponents. So let's write 4 over the 7th root of a squared using a rational exponent. Well, we know using the properties that we've discussed that the power is 2 and the root is 7. So we can rewrite 4 over the 7th root of a squared as 4 over a to the 2 over 7 power. And what we can do with that, since we know the properties of exponents, we can write that as a negative exponent as 4 times a to the negative 2 over 7. Let's do one more example with this. Let's write x times the square root of 5y to the 9th power as a rational exponent. Again, we know the power is 9, and this time it's a square root, so our root is 2. So that is equal to x times 5y raised to the 9 over 2 power. And that's how we can simplify it. Okay, let's do one more type where we simplify rational exponents. Let's try out simplifying, example. Simplify 8x raised to the 1/3 power times 14x raised to the 6 over 5 power. So how can we do this? Well, what are our properties of exponents? What do the properties of exponents tell us? Well, when we have factors of something, we are allowed to do what? If you have the same base raised to a power times the same base raised to a power, you can add those exponents. Well, first we need to simplify 8x raised to the 1/3 power. We know using the properties of radicals that we can write that as 8 to the 1/3 power times x to the 1/3 power times 14 times x to the 6 over 5 power. Well, the cube root of 8 is 2, which leaves us x to the 1/3 power times 14x to the 6 over 5 power. So we're left with 2 times 14, which is 28, times x to the 1/3 power times x to the 6 over 5 power. Now we need to add those exponents. We need to add 1/3 and 6/5. And we can do that by finding a common denominator to be able to add those. So not 26, 28. What common denominator should we use? Well, we should use 15. So 1/3 in terms of 15ths would be 5 over 15 plus 6/5 in 15ths would be 18 over 15. And so we can add those together and get 28x. 5 plus 18 is 23 over 15. At this point, we have done all of the examples and all of the portions of this section. Please go to Edfinity and work on your homework. And if you have questions, be sure to email me.